This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to today's discussion. We're diving into the world of interactive physics simulations, specifically a resource called Pushing on a Block. It's a fascinating HTML5 applet designed to teach dynamics.
Indeed, it's a great example of how technology can enhance the learning experience in physics, making abstract concepts more tangible and engaging for students.
The applet lets users adjust parameters like spring tension and friction. What's the pedagogical value of that level of interactivity?
It allows for experimentation and discovery. Students aren't just passively receiving information, they're actively manipulating variables and observing the consequences. This fosters a deeper understanding of cause and effect.
Exactly. It's not just about memorizing formulas, but about intuitively grasping the relationships between forces. Let's start with a general overview. The briefing document describes the applet as simulating a block being pushed by a spring. What are the main themes and key ideas it aims to convey?
The core idea is to illustrate the dynamics of forces acting on a block, primarily focusing on applied force from the spring, friction, and the resulting motion. It visually represents the interplay of these forces, making Newton's laws of motion more concrete.
The document mentions adjustable parameters. How do these adjustable features contribute to the learning process?
The adjustable spring tension, for example, allows students to directly control the applied force. They can see how increasing or decreasing this force affects the block's acceleration and whether it overcomes static friction. The sliders and combo boxes provide further control over other parameters, allowing for systematic investigation.
The applet uses HTML5 and JavaScript. Why is this choice of technology significant?
It's crucial for accessibility. HTML5 and JavaScript are widely supported across different browsers and devices, unlike older technologies like Java applets. This ensures that the simulation is readily available to a broader range of students, regardless of their devices or operating systems.
And the embeddable iframe code, what does that offer educators?
It simplifies integration into existing learning platforms. Teachers can seamlessly embed the simulation into their websites or learning management systems, making it a convenient resource for their students.
The document highlights the visual feedback, particularly the contact/red force, representing the normal force. How effective is this visual representation?
It's incredibly effective. Visualizing the normal force, which is often an abstract concept for beginners, makes it much easier to understand its role in determining friction. The changing color of the force vector based on compression or stretching of the spring is a particularly clever design choice.
The user interface seems quite intuitive. What are some of its key features?
Besides the adjustable spring and sliders, the draggable text labels are a nice touch. It allows students to customize the display to their preference, improving comprehension and engagement. The play/pause/step/reset buttons provide granular control over the simulation, enabling detailed observation and experimentation.
What are the potential learning goals of this simulation?
The simulation aims to help students understand the relationship between applied force and friction, visualize the normal force, investigate the conditions for overcoming static friction, and explore Newton's laws of motion in a dynamic context.
Who is the intended audience for this resource?
Given its placement within the Forces and Moments section of the website, it's likely targeted at secondary school or early undergraduate students studying introductory physics.
The accompanying study guide provides short answer and essay questions. What's the purpose of these questions?
They serve as a framework for guided inquiry and deeper learning. The short answer questions reinforce key concepts, while the essay questions encourage critical thinking and application of knowledge.
The study guide also includes a glossary of key terms. How important is this for student understanding?
It's essential. A clear definition of terms like dynamics, friction, normal force, and net force is crucial for students to grasp the concepts being illustrated in the simulation.
The FAQ section addresses common questions about the applet's functionality and embedding. How important is this type of support?
It's vital for user adoption. Providing clear instructions and answers to frequently asked questions ensures that educators and students can easily use the resource effectively.
The resource is openly licensed under Creative Commons. What are the implications of this open educational resource OER approach?
It promotes accessibility and reusability. Educators can freely adapt and share the simulation, fostering collaboration and innovation within the educational community. This aligns with the broader movement towards making educational materials more widely available.
The website lists many related simulations covering various physics topics. What does this expensive collection suggest?
It indicates a commitment to providing a comprehensive and interconnected set of learning resources. The variety of simulations allows for a more holistic and integrated learning experience, covering a wide range of physics concepts.
In your opinion, what are the strengths and limitations of this particular simulation?
The strengths lie in its interactivity, visual feedback, and accessibility. Limitations might include the scope of the simulation. It focuses on a specific aspect of dynamics. Further simulations could expand on related concepts.
How effectively does the simulation illustrate Newton's laws of motion?
It does so quite well. By adjusting the applied force and observing the resulting acceleration, students can directly experience Newton's second law, F equals m. The concept of inertia, Newton's first law, is also demonstrated when the applied force is removed. Newton's third law is less explicitly shown, but can be inferred from the interaction between the block and the spring.
The simulation emphasizes friction and the normal force. How does it help students understand these concepts?
The visual representation of the normal force as a red vector is particularly helpful. Students can see how it changes with the applied force and how it directly affects the frictional force. By experimenting with different surface types implied by the adjustable parameters, students can also explore the concept of the coefficient of friction.
How can educators use this simulation to promote inquiry-based learning?
The adjustable parameters allow for a wide range of experiments. Students can formulate hypotheses, design experiments to test those hypotheses, and analyze the results. This active learning approach fosters critical thinking and problem-solving skills.
What kind of experiments could students conduct using this applet?
They could investigate the relationship between applied force and acceleration, determine the coefficient of static friction, or explore the effect of mass on the block in motion. The possibilities are numerous.
What is the significance of this simulation being an OER?
It makes high-quality educational resources accessible to a wider audience, promoting equity in education. The open license encourages adaptation and improvement by the community, leading to ongoing development and refinement of the simulation.
What potential improvements or expansions could be made to this simulation in the future?
Adding more sophisticated features, such as the ability to change the mass of the block or incorporate different types of friction, would enhance its educational value. Including data logging and analysis tools would also be beneficial.
So in summary, this pushing on a block simulation offers a valuable, interactive approach to teaching fundamental concepts in dynamics.
Absolutely. Its accessibility, interactive features, and open licensing make it a powerful tool for educators seeking to engage students in active learning.
The visual representation of forces and the adjustable parameters are particularly effective in making abstract concepts more concrete and intuitive.
Precisely. It's a great example of how technology can transform the way we teach and learn physics. The open source nature also allows for continuous improvement and adaptation to meet the evolving needs of educators and students.
That was a great discussion. Thank you for your insights.